Okay, for this last problem, we're going to find the volume of the solid obtained by rotating the region enclosed by y equals x squared, y equals 12 minus x, and x equals 0. So the region is enclosed by these three graphs about the line y equals -2. So this one here, we do note that this is a different axis of rotation, right? This is an arbitrary axis of rotation. So we're going to have to keep that in mind for later on in the problem. And the first thing I want to do is actually just graph our borders, what forms the region of integration here. So let's do so. So we have something that looks like, so I'll just draw a big graph on this one, and on the next slide, if we need it, I'll sketch the graph again. So we have, let's say, so one of them has to go all the way up to 12, right? So we'll go by 4s. So this is 4, 8, 12, okay? 4, 8, 12. I did not put that 4 in the right place. 4, 8, 12. Then we have -4, -8, -12, which we probably won't need. This is a -4. That's a -4 as well. Okay, so what do we have going on here? So the first one is just a normal parabola, right? So we're basing it at 0, 0. We go over 2, up 4, that kind of thing, over 2, up 4. All right, so something like this, okay? So something like our normal parabola. That's the first graph there. Okay, so this is our x squared graph. And then our next one is 12 minus x. So that's 12, that's our y-intercept, and -1 is our slope. So it's going to have to cut through 12 and the other 12 here on the x-axis. So something like that. That was a pretty good line, actually. Okay, so this one here is 12 minus x. All right, and then so far we have these two things, these two borders here, and then we also have x equals 0. So that means our y-axis. That forms our third border. So the region that we're looking at is actually this thing right in here, okay? All right, so now if we look at it a little bit more closely, what we're going to have to do is rotate it about the y equals -2 axis, and -2 is down here, so here's our axis down there, right? So this is y equals -2, so that means that we're going to have to start our radii from down here. So that means, so here's the closer one, up to the bottom border of that region. So this is our little r. And then capital R is going to be from the axis of rotation all the way to the far border of our region. So that's going to be our capital R. Okay, so let's find those formulas. So we have capital R is going to be given by top minus bottom. So the top thing that we're touching is the line. So this is going to be 12 minus x. And then minus bottom, so minus whatever our bottom, the bottom point touches, which is the line y equals -2. Okay, so we're going to get that capital R is given by 12 plus 2, so 14 minus an x. All right, so now let's work with the little r. So that one's going to be given by, the u is the top, right? So that would be x squared, and then minus our bottom function, which is a -2. So we're going to get r is given by x squared plus 2. Okay? So now that we have formula for our radii, so those are our radii there, we need to figure out where are we integrating on, what interval, what x interval is this. So the way we can figure that out is finding where our graphs intersect. Okay, so that would be x squared and 12 minus x. All right, so let's figure that out on the next slide. So we want x squared to equal a 12 minus x, and that does so when x squared plus x minus 12 is equal to a 0. So that means x is going to be plus 4 and x minus 3. That's going to equal 0. So this occurs when we have x is equal to -4 or 3. All right, but if we look at our graph, these can't be the bounds because remember our graph looks something like this. I'll just sketch it real quick. So we had something like that, and it's bound by this here. So it has to be between 0 and whatever the positive value is, so that one is going to be our 3. We're going to kind of ignore that -4 there. Okay, so our interval of integration is 0 to 3. We're integrating along dx because our lines are vertical, right? And we're rotating about the line y equals -2. And our capital R is given by 14 minus x. And our lowercase r is given by x squared plus 2. All right, so let's set up our volume integral. So we have v is equal to pi times the integral from 0 to 3 of capital R squared, so 14 minus x, quantity squared, minus little r, x squared plus 2, quantity squared, and then our dx there. Okay, so let's continue this on the next slide where we have more room. So we have v is equal to pi times from 0 to 3, 14, try and draw 14 minus x squared in there, and then minus our x squared plus 2 squared. and then a dx, okay? So when we do that, we're going to basically just distribute everything out. So we have integral from 0 to 3 of, and then this turns into a 196 plus an x squared minus a 28x, okay? And then our second one here is going to be minus an x to the fourth plus a 4 plus 4x squared. And then we have a dx at the end there. Okay, so when we distribute the negative sign, we'll do that on the next step, okay? So we get v is equal to pi times 0 to 3, 196 plus an x squared minus 28x, and then minus this x to the fourth minus 4 minus a 4x squared and dx. Okay, so now let's see what we can do with this. So we have v is equal to pi times integral from 0 to 3 of 196 minus 4 is going to be a 192, positive 192, and the x squareds are going to become a negative 3x squared, not x cubed, x squared, and then we have a minus x to the fourth still there, and a negative 28x. Okay, and that's basically it. We can't combine any more like terms, so what we're going to do is just integrate. So we have v is equal to pi times 192x minus an x to the third, and then minus an x 1 over 5, x to the fifth, and then minus a 14x squared, evaluated from 0 up to 3. Okay, so basically for all of these, we have an x term of some sort. So when we plug in that top integral, or limit of integration, that'll be fine. But then when we plug in the bottom one, we're basically just going to be subtracting 0. So we kind of can just forget about it. Okay, so what we're going to get is, I'll continue this on the next slide so we can do the rest of the math on there. So we have v is equal to pi times 192x minus x to the third minus a 1 over 5 x to the fifth minus a 14x squared, and evaluated from 0 up to 3. Okay, so v is equal to pi times 192 times the 3 minus 3 to the third minus a 1 over 5 times 3 to the fifth minus a 14 times 3 squared. Okay, and like I was saying, this would just be minus 0 anyways, so we don't have to worry about that term there, which is good, because if we had more terms, then that wouldn't be too pretty. So anyways, so this is going to be pi times, and when you multiply 192 times 3, we get 576, and then minus a 27, and this is 3 to the fifth is a 243 over 5, and then minus 14 times 9, which is a 126. Okay, so if we continue here, we're going to combine all of those. So 576 minus 126 is a 450. And then we have our minus 27 minus 243 over 5. So if we continue on, we don't have too many more lines to go. So this is pi times a 423 now minus 243 over 5. Okay, so this is equal to, v is equal to pi times, and then 423 times 5 is a 215. And this will be minus 243 over 5. So we ultimately get a 1872. There we go, 1872 over 5 and times pi. All right, and that is finally it. We have made it. All right, so that wraps up our video, our practice problems video on volumes of revolution. I hope that helps, and happy studying.
Now that I feel it's time to spend the night away, I want to know, do I